Good afternoon. Welcome to Algebra 2. Hope you're enjoying the long weekend. And what is it? 5-day weekend. It's pretty nice. 5-day weekend. So we are going to look at word problems today. The homework that's due on Monday is assignment 3.6C. Solutions are already online. It's word problems. Now, when it comes to solving word problems, usually what you hear from math teachers is, oh, there's going to be word problems on the high stakes tests like the PSAT, the SAT. You know what? How many of you, I won't turn the camera on you, but how many of you are willing to admit that you're kind of tired of that justification for doing well in math? It's like, I've heard that. Okay, thank you for admitting that. Just yesterday after conferences, it was last night, I came home, my daughter asked me if she could show me a YouTube video. It's 5 minutes. Dad, can you watch a 5-minute video with me? It was about school. And it's this guy on YouTube saying, hey, what really is the point of school? Why are we really doing this? Is it worth our time? Is it worth our time? Yeah. So, and I was listening to that, and you know what? The teacher inside of me felt like, pulling the cord and saying, this is poisoning my daughter's mind. We shouldn't be watching this. But then I realized, you know what? Let's listen. I said, I'm going to listen. I controlled myself. I listened to the argument. And it is kind of sad that a lot of times people don't really get a compelling reason to really sacrifice themselves and pour themselves into school. I think that when we look at word problems, we have an opportunity to look through a window and to see something that you might not ordinarily see. Here's what I'd like to argue. That there is actually a good reason for us to be here today, more than just getting ready for the high stakes tests. Something that goes beyond that. I'd like to propose that for hundreds of years, mathematicians have gotten out of bed, not because they want to get high scores on tests, because they care about rescuing people from suffering. Do you have friends? Do you care about anyone?
No.
If just think about these people you care about. If they were suffering and you found out that mathematics could be part of the solution to protect them and rescue them from suffering, would you want to be able to help them?
Yeah.
Yeah. Now, one thing that happens when we go to word problems, you've got people coming along and saying, you know what? I think that words should not be allowed in math class. Math class should just be about numbers. No words allowed. Well, guess what? The people who are suffering, you know how you know they're suffering? Because they complain using words. So thank you, I heard that. Thank you. When people are suffering, they're going to describe their turmoil with words. And so it's going to be your job to take the words and turn them into mathematical models. So when I ask you to put words inside boxes, it's because in reality, when people are suffering, you're going to have to be able to connect the words to the equations. A word equation to an algebraic equation. Now in this problem, we have a youth group with 64 members going skiing. And each of the 12 chaperones will drive a van or a car. The vans can seat 7 people, the cars can seat 5 people. How many of each type of vehicle could transport all 76 people to a ski trip area in one trip? And you're saying, where's the potential for suffering, Mr. Royce? What does this have to do with your impassioned speech? Well, friends, if we don't get this right, then people who sacrificed for months to save up enough money to go on the youth group ski trip are not going to have a vehicle. They're going to be standing there in the cold all weekend, no one to take them to the ski hill.
That's so sad.
We don't want that, friends. You don't want people who love people. Do not let their friends stand out in the cold all weekend without a ride to the youth group ski trip.
Hey.
Now, friends, so let's put words into boxes to figure this out. Now, all equations, and some people think that equations just come out of nowhere, but equations are actually based on ideas that are true. And one idea that appears to be true is that, and I'm going to use NO as an abbreviation for number. The number of vans, please write that and put a box around it. The number of vans plus the number of cars, it's undeniably true that the number of vans plus the number of cars has to equal the number of adults. That's because we're not letting your high school students, you have your driver's license, but we're not going to let you drive the van you have to be an adult leader to actually drive the van, even if you have a driver's license. So we're going to put a chaperone on each vehicle. Now, we can call that, if we can translate it from words into algebraic symbols, every one of these should be either a number or a letter. The number of vans, is that known or unknown at this point?
Unknown.
It's unknown, so I'm going to call it V. By putting a V here, I'm basically saying let V represent the number of vans. Don't say just V equals vans. What is it? V equals the color of the van? Does V equal the air temperature in the van? No, it's the number of vans. C is the cars, number of adults, it's got to be 12. So we have E1, our first equation.
Oh.
Okay, that is our first equation in our system of 2 equations and 2 unknowns. Now they give us some other information. Vans can seat 7 people. So here I'm going to, and you're probably writing a little bit smaller. The first time I write big so the camera can see it, but then I tuck it away. To focus on the words in the second one, what often happens in the real world is that you start out with an idea that's developed in broad strokes, and then you give it more detail. And in broad strokes, we know that the number of people on vans, we're going to go to another color that will probably show up pretty well on the camera is red. So NO, number of people in vans. The number of people in vans plus NO for number of people in cars has to equal what? Conceptually, that's got to be what? People, by the way, are students and chaperones combined. I don't know if you're aware of this, but chaperones are people too.
I don't really think
So
so.
the number of people in vans plus the number of people in cars has to equal what, friends?
76.
Yeah, which is the total number of people. I can either write total number, I'm going to write total people. Now, this is a broad strokes idea. We can make it more specific, and this may seem like overdoing it with the words, but the concepts here, that I'm going to actually draw 2 boxes for this first box and 2 boxes for the second box. The concepts here can get confusing unless we're verbally clear. I think that if you wanted to calculate the number of people in the vans, I think you'd have to find out how many people are there per van, people per van, and multiply it by what?
Wait, hold on. 7 times.
Just conceptually, not numbers yet. If I want to find out how many people are going to be riding in vans for this trip, well, I'd have to find out how many people are there per van. We're going to assume that the vans will all be full and the cars will all be full. So it'd be people per van times what would give you the total number of people riding in vans? Did you say number of vans?
Yes.
Good. So thank you, Jana.
Anytime.
So, famous now. So, it's people per van, in fact, no. Number of people per van. Per is an important word mathematically. Number of people per van times number of vans plus, and then write 2 boxes filled with words for the second one. Per car, number of people per car times the number of cars. That's the total number of people, which they told us is 76. Okay, so as far as setting up this system goes, we've already got V plus C equals 12. Number of vans plus number of cars has got to equal 12. That's equation 1. And we also know that based on this, is the number of people per van, is that known or unknown? Is that a known or an unknown? If it's known, we'll give it a number. If it's unknown, we'll give it a letter. Actually, they do tell us vans can seat 7 people. So this is actually 7 number of vans. We already use V for that. So this is 7V. I'm going to write this in red. Under this, I'm going to write 7. Come on, let's go red. Okay. 7V plus, and the number of people per car is given as 5. 5C equals 76. So it's 7V plus 5C equals 76 is equation 2. Now we have a system. We've taken the people who we want to protect them from suffering. We've listened to their words, and now we've come up with equations. Now, it's actually pretty straightforward. Just do the algebra. Go ahead and multiply the first equation by -5. Go ahead and solve for B and C. So try to finish it on your own. Just solve by elimination or substitution. It's up to you. You've got to find a method to solve the system. I'm just going to turn off the camera while you're solving, then we'll come back together, see how we do. And if you multiply the first equation by -5, you probably got V is 8 and C is 4. But because we care about these people understanding what's going on, and I did turn the camera back on, didn't I? Yeah, I did. So we actually express our answer in words, words that the people who need to make decisions to stop suffering and prevent suffering can understand. Look, 8 vans and 4 cars is what we need. 8 vans and 4 cars could transport all 76 people to the ski area in one trip. Or basically, you can say it more simply, but please use English. Say, we need 8 vans and 4 cars to transport everyone to the ski trip. Any questions on our first example? Yes, go ahead, Peter.
Could 3 vans and 11 cars work?
You say, does 3 vans and 11 cars work?
I mean, yeah, it technically works.
No, because then we wouldn't have enough drivers.
Oh, I understand now.
Okay.
I don't know how I got
So
that.
then we'd have, just imagine the suffering that comes from a van rolling down the road with no driver.
I mean, I don't know how to get on the road without a driver.
Well, just
Put it in neutral.
put it, it'll get moving.
Yeah.
You can get it moving without a driver.
Let's see where you're coming down.
Further questions? So, especially in the modern era of Western civilization, mathematics was about reducing suffering. We're in the postmodern era right now. In the pre-modern era, it was a different narrative, a different story that motivated mathematicians. Some believe the modern era ended right after World War II, when people lost confidence in the ability of science to reduce suffering, and with the atom bomb and everything, people became a lot more skeptical of authority figures, external authority. I mean, think about the chapel message we heard today. In the postmodern era, there is this theme of being really skeptical of whether or not authority figures can be trusted. So postmodern era, things are a little bit different, but we're just kind of living in the modern era in today's math class. And there's actually a lot of good things in the modern era that should not be so easily discarded. Let's go on to our next example. We are on number 2. So sometimes you don't have to do a verbal model because they tell you what X, Y, and Z represent graphically. Now in this problem, we used words to attach meaning to V and C. Sometimes mathematicians use graphs to attach meaning to letters. So here, it's actually not quite as hard. We can get a system of equations based on not thinking about ideas. And who knows, maybe suffering is involved in here. We're not sure. It's not as clear. It's more of a pure geometry problem. But we do know that this is a regular 5-pointed star. There's a regular pentagon here, and that the measures of the interior angles of a pentagon do add up to 540. So all of these are equal to Z. That's going to be the third equation, actually. Let's do these in reverse order. We know that 5 of these Z's adds up to 540. Now, another thing we know is that the 3 angles in a triangle have to add up to something. Does anyone remember what that number is? 180. So the X and the 2Y, the X and the 2Y have to add up to 180 degrees. And the third thing that we know is that Y and Z are supplementary angles. Together they form a straight angle. So Y plus Z also has to be 180 degrees. You don't need the degree symbol to do the system. So class, since the value of z is pretty accessible here, in fact, for the sake of time, I mean, we've been talking about some deeper philosophical issues today, so I'm gonna kind of push us through to save time on the math, but if you divide by 5, you get 108. So it turns out that z is 108. And if you substitute z equals 108 into this first equation here, you could probably do it in your head. I mean, think about it. 108 plus what is 180?
72.
It's gotta be 72, so y is 72.
You're smart.
And then, just trust me on this, if you put a 72 in for y, take 72, multiply it by 2, subtract from 180, you'll get x is 36. So in this,
That makes sense.
yeah, so on this problem, you didn't really have to do much, it wasn't very verbal. But I wanna do another verbal model so that you get more practice with that. Yeah, Peter?
So how could, if it was y plus z equals 180, then how could x plus y times 2 equal 180?
It's just a coincidence, it doesn't always happen that way. But you can see it in the geometry. We know that x plus 2y is 180 because the angles of a triangle have to add up to
Oh, that's
180.
an x, okay.
And then
instead
y-
of the z.
Yeah, and, oh, it's two y's and an x. All right, so let's go to the next page. Last one that we're gonna do for today. We just wanna set up the system. I know you can solve the system. But we have here, food. It's a food truck. Where's the suffering angle? Sometimes people suffer when they don't get food every 30 minutes or so. So this could be a big issue. We're hoping there's a food truck that can supply us here when we get hungry. A food truck sells hot dogs, hamburgers, and drinks. Hot dog, 2 hamburgers, and 3 drinks can be purchased for that. Okay, they've basically given a verbal equation here. Make that blue. This green verbal equation, one of each is this much. And then there's gonna be a red equation, 2 hamburgers and 2 drinks cost $10.50. So it looks like the idea is for all of these, it's gonna be like on the vans, it's gonna be like cost per, we'll abbreviate hot dogs as dog, cost per dog times number of dogs. That'll be the first pair of boxes. Cost per burger. So don't just write burger. I think in the past, maybe you've been like, not really a big fan of words in math class, so you oversimplify it to just burgers. No, it's not the weight of the burger, it's the cost of the burger. Or cost per burger, really. I should be using per here, cost per burger times number of burgers. Plus cost per drink, it's a ratio, it's like a slope, times number of drinks. So add these up, that gives us the total cost, total United States dollars. So now there's a system to this. We ask ourselves, known or unknown? Is the cost per dog known or unknown? Well, that's what they're asking. How much does a hot dog cost? So we'll call D for hot dogs. Okay, so on the first equation, it says 1 hot dog, so times 1, plus, and I'm glitching a little bit, so that means I have to save. So see if we can finish translating the verbal model into an algebraic model. Burgers times, so 2 hamburgers. Cost per drink is unknown, but the number of drinks is known in this blue model, and that costs $14.50. So if you're putting together a system, the first equation in the system is D plus 2B plus, whoops, dog and drink. I messed up. You got hot dogs.
Dog can be H.
I should have used H for hot dogs. Yep, thank you. So we're gonna delete that. We're going H for hot dog. It's kind of scary, don't watch it. We'll use that to rewind, watch that over and over again. Hot dogs plus. So class, you know what? I don't often ask you to stay later, but I just want to make sure you get the system. It's hot dog plus 2 of these plus 3 drinks is $14.50. The second equation is H plus B plus D equals $7.50. And the last one is 2H plus 2D equals $10.50. That's what you'd have to solve, hopefully with RREF. The homework is due on Monday, 3.6C. Have a good night.
You too.
Wait, can you